And we're live.
We're live. Okay. Hello. This is Ariel from Zcash. Hi, Zuko. So this is our live stream about zk-SNARKs. And what I thought I'd do is kind of start with a semi-planned, semi-random rant about interesting things about proofs and snarks. But please interrupt me with questions or comments according to what you're interested in.
Wait, are there a bunch
Okay,
of listeners, and how can they interrupt? How can they express
so I
questions?
think
So people can post questions as comments in the YouTube live stream, or there's a chat box, and we'll keep an eye on that.
okay.
How do we see the
So
box? Sorry to interrupt.
I think you can see it if you go to YouTube. You go to like the YouTube address
I don't know what the YouTube
where it's at.
Can you post that page?
Yep. Posting that in our little chat here. Just don't play the audio because then we'll have feedback.
Right. Okay, so I was actually lately looking at some, I wanted to say a few words about, these really early works that that started this this SNARK stuff. So can you see my screen?
Yes, I can.
Right. So I stumbled upon this this old kind of explanatory paper by Laszlo, sorry, Laszlo Babai, one of the first people involved in this sort of stuff, and he gives a nice example here. So King Arthur has 150 knights and 150 ladies in his court, and he says, well, it would be better if we had 150 couples. So he goes to his magician Arthur and says to Arthur, hey, I have these 300 these
Merlin.
men and women. Yeah.
The magician is Merlin.
Merlin is the magician. So Arthur goes to Merlin and he says, hey, I have these 150 knights. For each one, here's the ladies he's interested in. Each one is interested in. And for each one of the ladies, here is a list of the knights that she likes. Please find what's called a matching. So find a way to make 150 couples from them so that each couple likes each other according to these lists. So Merlin, who is very, very powerful, he basically checks all different combinations. So this is 150 factorial, so a lot of possibilities. And he sees that there's no matching. There's no way you can pair everybody such that every pair will like each other. And he says to Arthur, there's no way to do it, I'm sorry. Here and here is like all my notes that I went through all the possibilities, and of course this list of possibilities, Merlin's notes, it's too big to fit in the castle. And Arthur says, well, how can I trust that you really check? You probably missed something, So this seems like a hard problem. Like, how can Merlin convince Arthur that he didn't overlook anything, or he's not hiding any good matching? And so this was really a ground breaking work, what's called the LFKN protocol by Lund, Fortnow, Carlo Finissan. This is really the work that kind of started this whole field, in my opinion. So they gave a way where Merlin can very quickly convince Arthur that that really there's no good match. And at a high level, the way you do this is by, their basic idea is by moving the problem to the language of polynomials, you could say. And so the question is, what's good about polynomials? Well, so one basic thing about polynomials is that if two polynomials don't agree all the time, then they won't agree most of the time. So as one example, suppose I have a really long string, and I tell you, hey, this string, it's all zeros. I checked it and it just has zeros. So the question is, like, how can you, well, either trust me or be sure I'm not overlooking something? Because maybe this string just has like 1 0.
You mean a single one?
Yeah, a single one. So it seems like if it's just, you don't know anything about these strings and you want to kind of distinguish between the case where it's all zeros and there's only one non-zero, it seems like you really have to go through everything, right? If you just like, okay, I say I'm just going to randomly check 5 places, there's a really good chance you'll miss this one non-zero. And this like non-zero, think of it like in our example, think of it as maybe the one good matching that Merlin maybe either missed or is hiding. But the thing is, when you move to polynomials, so if I have some polynomial, like say x squared minus x, so it's not the 0 polynomial. It's not just the polynomial that always returns 0. Well, so it's going to be different from the 0 polynomial almost everywhere, right? So on 0, you're going to get 0 because it's like 0 minus 0. On 1, you're going to get also 0. It's like 1 squared minus 1. But from that point, you're not going to get 0. So if you have a polynomial and you want to check if it's always 0 or not, then in that case, you are allowed to just kind of choose a random point, like a random x, like, I don't know, you'll choose here x equals 5 or whatever. And it's enough to just check, do a spot check. So this is like really the central point in all this work over the last decades about these like succinct proofs. That once you move to the language of polynomials, you can just do, it's enough to do like random spot checks. And this ultimately has a lot to do with these proofs we get for Zcash, which are only a few hundred bytes long. Right, and so it's no accident that if we look at our new like SNARK explainer page, and we look at the SNARK explainer series, the word polynomial appears a lot.
I have a question.
Yeah.
The property of polynomials that allows you to check most points should vary from 0. Is the most points characteristic something that's like directly related to the fundamental theorem of algebra? Is it something you can just know?
Oh, yeah,
you know
exactly. So exactly, I think the fundamental theorem of algebra says that a polynomial of degree d can have at most, let me stop sharing for a second, can have at most d zeros. So what follows from that also is if you have two different polynomials, they can agree on at most d points. Why? Because if you do one minus the other, and they're not the same polynomial, you're going to get some polynomial that's not always, that's not identically zero. So it can't have many zeros. It can only have the degree zeros. And well, what are its zeros of this f minus g? It's exactly the points where f and g agree. So this is kind of what happens in the SNARK, that the prover has to come up with two polynomials, and he can't just choose any polynomials he likes. You make him choose them in a certain way, and then the way it's constructed is, if his transaction is non-valid, he will not be able to make these polynomials identical. So if his polynomials are now not identical, if you'll just choose a random point and check if they agree on that point. If they're not identical, with very high probability, you'll catch him. You'll try a point where they're not equal. All right, so yeah, I'll go on, but yeah, let me know if there are any questions or remarks. So, but now kind of the big challenge in this whole field is who goes first, because if kind of the one who's verifying the proof tells him, okay, I'm going to check you at this point, then he can just construct polynomials that they're not going to be identical, but they are going to agree on that point. So here there was what's called the classical approach, which was kind of pre-SNARK, which was the SNARKs that were not yet really practical. And what they said is kind of, okay, we're just going to make him commit to all his answers in advance. We're just going to make him write, okay, what are you going to answer if I ask you at point 0? What are you going to answer if I ask you at the point 1? And so forth. Yeah, and I think I won't get into that, but that creates all kinds of a few complications. One of them is that, like, how do you know? Maybe I'll share for a second again. Well, one complication is, how do you know if he's writing all his answers in advance? How do you know he's writing answers that correspond to some polynomial of low degree? So, for example, if you look at this string, like 0, 0, 0, 0, 0, 0, 1, and then all zeros, there's no polynomial of low degree that will give you these values. So here comes like kind of the heavy component in kind of the zk-SNARK. Yeah, well, the previous thing you could also technically call them zk-SNARKs. But like the pre-Zcash, the style that Zcash is using, SNARKs. So then kind of what you had to do was this thing called low degree testing, which was what's low degree testing? So I give you like this long string of values, and just randomly, and you don't have time to read all the values here. You just want to check a few of these values, but you need to somehow decide, well, is there some like polynomial, low degree polynomial, like say of degree 2 or 3, that will give me these values, or at least give me something very close to these values. So this is like there's a lot of really ingenious work that really nice math that, you have this really long table of values, and you only have time to look at a few of them, but still you want to somehow be able to say, yeah, this table, there's some low degree polynomial that describes it. Anyway, the reason but this low degree testing, it's a really heavy component. It's like, if you want to, at least currently, if you want something that, the probability of cheating is like 2 to the minus 100, you have to write a lot of stuff, maybe a megabyte, or I'm just throwing these numbers, but it's big.
So does the new STARK approach, does that still use low degree testing?
Yeah, so as far as I know, the STARKs are mostly based on what's called the classical, these classical techniques, with some improvements, but yeah, the heavy component there is this low degree testing.
Okay.
Anyway, so the new thing that happened in the last few years is, so why were we in this kind of mess? Mess is a negative word. There's a lot of really nice stuff but why are we in this situation where we have to check if this huge table corresponds to some polynomial? Because, again, the problem is, if we tell the prover in advance where we're going to check him, he's going to make something that is good on that point. So we can't do that. And then this idea came in a few really nice works, like a decade ago or a little less. One really, I just want to mention some, give some credit. One really nice work of Yuval Ishai, Eyal Kushilevitz, and Raphael Ostrovsky, and some nice works of Jens Grof. This was this idea that, okay, yeah, we'll just tell the prover, we will tell the prover in advance what point we're going to check him on, but we're going to give him this point in encrypted form. So this basic idea, this was kind of what enabled to kind of cut the fat from the previous constructions already from the 90s. And so basically this whole huge part of the proof where you have these commitments of the prover to some large table, and you have the proof that this table is really close to some polynomial. Basically this idea that, yeah, we'll tell the prover in advance what our challenge point is, but we'll give it to him in encrypted form. So this allowed kind of most of the heavy stuff in the proof to kind of just be thrown out. But of course there's the question, can you really do this? Does this really make sense? And the basic problem seems to be, well, if I give him kind of the point, like the challenge point. So think of it, he has some maybe one polynomial or a few, but let's say one, like polynomial p, and I have my challenge point s, and I want to get like p evaluated at s. Oh, and I'll sidetrack by saying, okay, and you could also say, all right, if you want to know p at s, just ask him for all of p. But again, there are two problems with this if you want to get zk-SNARKs. One is that this p can be huge, and you don't want these huge proofs. And another problem is that, right, we want to get zero knowledge. So for example, in Zcash, this, like, if you'll get all of his polynomial, that will have a lot of information on his transaction, on his address, on the amount of the transaction, and so forth. So you want to be able to just get, like, p evaluated at s for these two reasons. One reason is that, well, it's a lot less to. It's very short. It's just the polynomial at one point. And another reason is the zero knowledge. The thing is that, like, once you have like a proof system, intuitively you could say, once you have a proof system where the proof is very short, then when the proof is very short, there's like less places where sensitive information could leak. So basically, kind of the zero knowledge, which is kind of the magical feature, or kind of the magical feature, the feature that's very prominent. Actually, technically, when you get into how it works, once you get to very short proofs, it's like getting the zero knowledge part is really easy. And I want to just, I like to give credit to some classical works, so I'll screen share for another second. So this was basically, this is really one of the, it's called, the name is misleading because the paper name is called like a note. But this is really a beautiful, this you could say is like, yeah, this is kind of one of the foundations of like the SNARKs, or STARKs or SNARKs. This is more in the context of STARKs at that point. Basically, what this paper said is that, basically just it formalized this intuition that once you get short proofs, then adding the zero knowledge part is can be done, oversimplifying a bit, but can be done with easy tweaks. Okay, but that was all part of a sidetrack a little. So the point we were at, and again, if there are any remarks or comments or questions, I'd be happy to get them, but otherwise I'll just continue. So kind of the point we were at was, okay, there's now the verifier is giving the prover this challenge point in encrypted form, and the question is, all right, if the challenge point is in encrypted form, how can the prover like the polynomial on it? And here comes, what I think is the, if you have to choose like one thing to say how does SNARKs work, here comes the, I think the biggest thing, if you have to choose one, which is this idea of homomorphic encryption, or homomorphic hiding, as I've called it. I called it hiding instead of encryption because in encryption you can always go back, you can decrypt. In hiding you can't necessarily, like, there's no decryption key. and that's not important for this context. So what is this like homomorphic encryption or homomorphic hiding? I want to go over like the first post in the series. So like the idea of a homomorphic hiding or encryption is, so what do I mean by homomorphic hiding? So it's some mapping that takes your input x into an output e of x, and what properties does this this e of x have? So first of all, it hides x, meaning that for most x's, if I just give you e of x, you can't find x from that.
I thought there was
yeah?
a technical problem here, which is the reason why encryption has to be randomized, which is that if you have a deterministic encryption function, then you can do a brute force search for the input. I guess that's why it's for most x's rather than.
Oh yeah. That's exactly that's a very good point. This is why you only get this most here.
Okay.
I
guess there's a more formal way of saying that because.
So I'm not so this kind of notion of homomorphic hiding is something I invented for the series. I haven't seen it, so I don't know if there's really a concept of some encryption where only most x's are hidden. I don't know if there's. So I think this can be formalized.
Yeah. So this is just giving you an intuition for how the protocol is constructed, and then if you have a particular instantiation, you have to do the hard work of proving it for that instantiation, rather than using a homomorphic hiding as an abstraction with its own security properties.
Well, yeah. So this is an abstraction I've used for the series. I haven't seen it, but now that you mentioned it, I mean, it could. I wouldn't rule out that you could use this abstraction to maybe, simplify or at least kind of modularize the SNARK proofs.
Okay.
So this is essentially what was done in the BCIOP paper. They refactored the original constructions, separating the algebraic parts involving probabilistic testing of low degree polynomials from the cryptographic part with crisply characterized requisite properties that the knowledge of exponent discrete log construction is conjectured to fulfill.
So could you maybe explain a little about how they do this separation? So
they define the notion of linear PCP, which is a proof system consisting of just two rounds. A verifier asks a query and gets a response. And it is sound only in the scenario where the response is known to be a linear combination of the queries. That is, the prover is committed to writing down a string, and then the answer is the inner product of the queries with that string.
Yeah, so I'm wondering.
In particular, the polynomial-based constructions that underline the QAPs yield such a proof system, and so far this is just algebra in crypto.
Yeah, but I'm wondering. I don't know that paper well. Is there some statement there that if you have a linear PCP, then under certain assumptions you have always a SNARK? Is there something of that form there?
What they show is that any linear PCP can be combined with any encryption or encoding scheme that has the requisite homomorphic properties in a black box way. And the combination of any such linear PCP and any such encryption or encoding scheme gives you a SNARK, where the particular properties required from the encryption or encoding scheme, those are well defined and somewhat subtle. They also differ between the publicly verifiable
The
SNARK
designated
case, let's say of
verifier
interest
and
is Zcash, and the somewhat simpler case where it's a designated verifier. You're only trying to convince someone specific.
so
Okay.
there.
So the
Mhm.
crypto part of that is where the knowledge of exponent assumption or the linear.
The knowledge of exponent assumptions come into justifying one particular instantiation of the crypto part.
Right.
A good candidate we have.
I see. What was the name of the paper there? BCIOP, did you say?
Yes, Bitansky, Chiesa, Isha, Ostrowski, and Panet.
Thanks.
So yeah, but so do they talk about the knowledge of exponent assumption in that paper, or did they give some other characterization of encoding schemes that is sufficient for SNARKs, or?
The requisite properties for several variants of SNARKs. And then they give several candidate instantiations, including in particular the one that we know and love based on knowledge of exponent.
Oh, okay, but it's not like a generic theorem that linear PCP plus this encoding equals SNARK. It's this linear PCP plus the, okay.
It is a general theorem. They find the cryptographic primitives needed for the algebraic part and for the cryptographic part. And then they they prove a general composition theorem of these primitives, specific schemes that indeed fulfill the requirements of those primitives. In particular, the QAP scheme gives a linear SNARK, as do several others. And knowledge of exponent and the encoding scheme based on it gives the requisite cryptographic part. But there are alternatives. For example, a recent paper of Bonnet al. Used the same framework with an encryption scheme based on lattices. And they combined that in that generic way with the algebraic part to get what is morally a lattice-based quantum resistant SNARK, but it's a SNARK in a more restrictive sense, is designated verifier, non-adaptive. So they use different lemma in the BCIOP paper and get something weaker in terms of functionality.
Yeah, well, I guess the designated verifier, it's easier to, it's maybe cleaner to, yeah, okay. Right, so anyway, just to kind of go back to the, all right, so homomorphic hiding, again, what I mean by it here is that it's kind of like encryption in the sense that given E of X, it's hard to find X. But the more kind of special property of it is that if someone knows the hidings of X and Y, you can get from that hidings of arithmetic expressions in X and Y. So for example, you can compute E of X plus Y from E of X and E of Y. Okay, and then like the question is, well, so how do you get such a function E? So a simple example of that is, so I'll assume here a little knowledge. But basically, if you have a group where the discrete log is hard, and you map A to G to the A, that's going to be a homomorphic hiding. Why? Well, the two basic things are, because the discrete log is hard, when you only see g to the x, it's hard from that to go back to x. And the second property is, so say I give you now e of x and e of y. So now I want you to, and you want from that to get e of x plus y. Well, that's going to be easy, because when you multiply things, their exponents add up. Simply meaning that if you multiply g of x and g of y, right, then that's going to give you g of x plus y. And now you're maybe wondering, okay, this looks easy for addition. How can I get something like this for multiplication? Like, how can I get such a scheme where given e of x and e of y, I can get e of x times y? It turns out from something called pairings of elliptic curves, you can do this. Or you can do something that's very, very similar to this. And that plays a crucial role in SNARKs. But anyway, let me go forward to the point where, for which I got to all of this. So, right. So what were we talking about? We wanted a protocol where, so say you have here kind of Alice, think of her as the prover, and Bob, think of him as the verifier. We were in the situation where Bob had some challenge point S, and he wanted to know, and Alice had some polynomial P, and Bob wants to know P of S. But again, the problem with just asking Alice, please tell me P of S, is that Alice could, after seeing S, Alice could say, okay, I want, I'll choose my P according to the S you gave me. So the result will be something that I like. So again, so we want some way for Bob to get P of S from Alice without kind of disclosing S. Right, so how can you do such a thing with this homomorphic hiding? Well, the idea is now that Bob will send Alice, so before I said he'll send Alice kind of just the hiding of S, so that won't be enough, so he'll send Alice kind of the hidings of all these elements, the hidings of 1, of S squared up to S to the D. And now, I don't know if I want to get kind of to the exact equations here, but the point is that because it's a homomorphic hiding, Bob can compute the kind of the hiding of P of S. Sorry, Alice can compute the hiding of P of S just from these guys. So this gives you a way to kind of give the prover a challenge point and have her respond to that challenge without being able to be adaptive, without being able to craft her answer according to the challenge, because the challenge is given in encrypted form.
If we're giving the hidings of all of the powers of S, don't we have to be worried that that's quite a lot of information and that it potentially could be easier to find S?
Right. Yeah. So that's a great question. So yeah. So you really have to make stronger cryptographic assumptions. So you cannot just assume the discrete log is hard. Kind of. You have to make this what's called the D-power Diffie-Hellman assumption, which says that even if I give you all of these, actually what you need for the proof, you know, is that if I give you all of these, not only can you not find S, in fact, you need to assume if I give you all of these, you cannot even compute E of like the next guy. You cannot compute E of S to the D plus 1. So yeah, you need to assume that, and that is a stronger assumption. There actually is a very acute algorithm for, you know, actually for finding S out of these guys that's slightly better than just the algorithm that will find S only from this guy.
Oh, okay. I'm feeling pleased with myself for working out that that was an issue without having read the footnote. I did review this at some point, but I forgot.
Yeah, for predicting the footnotes. Yeah.
And that is the knowledge of exponent assumption?
No. So.
Okay.
So the Pinocchio SNARK that we're using actually needs 3 assumptions that are slightly non-standard. So what is the knowledge of exponent assumption? But you guessed the next title. Or here I call it knowledge of coefficient assumption, just because I'm using this notation here where I'm writing alpha times g instead of g time to the alpha. Like I'm writing the operations additively. So let me actually say a word about why, before I say what the knowledge of exponent, or here I call it knowledge of coefficient assumption is, let me just say a word about why it comes up. Well, wait, suddenly I mixed a few things. Let me think about it for a second. So right, so we had this protocol where, you know, Bob kind of sends an encrypted challenge, like he sends kind of an encrypted form of S, and then Alice is supposed to give him back E of P of S. But now, so this homomorphic hiding, it creates a situation where indeed Alice is able, if she wants and is nice, she's able to compute this thing from these guys. But that doesn't mean that she has to, or that she will. So, right, if we're thinking about such a protocol, again, the high level, I'll remind for a second again, the high level idea of this protocol, which is kind of the cornerstone of the SNARK, is that it's a blind evaluation protocol, which means Bob has some point S he likes, and he wants to get P of S for Alice's polynomial P, and he wants to get this without having to show Alice S. So this is why it's called a blind evaluation protocol, because Alice is evaluating P on S without seeing S. All right, so anyway, the fact that Alice can compute like E of P of S from these values doesn't mean that she will. You know, maybe she'll just, you know, give Bob some completely random, unrelated value. Or maybe she won't be that random. Maybe she will give him some value that looks like E of P of S, but it won't be for a P of degree D. It will be for some function that's not a polynomial of degree D. Yeah, for example, maybe it'll be like a function, she'll use some function like this, which is very much different from any low degree polynomial. It's just all zeros, it just has this one out of nowhere, which is very different from what so the knowledge of coefficient or exponent assumption is something that forces Alice to really answer in the protocol according to some fixed polynomial. Yeah, I just thought it's a good point to stop to see if there are any remarks or questions before or instead of diving to what this knowledge of coefficient assumption is.
So I have a question. So
yeah, good.
You've got to stop in 4 minutes anyway, so it's a good time to recap instead of diving.
Oh, okay.
Oh, okay. But should
do we have time for my
Dare
question?
ask her a question or?
So I guess the reason why the proving key is so large is that it needs D powers of S, and D is the degree of the polynomial representing the circuit. So that's going to be
exactly
linear in the size of the circuit. Is that right?
Exactly. So, right. So actually, this is like a good thing to say that, you know, SNARKs are this non-interactive thing, and here we're talking about like interactive protocols. So eventually in the SNARK, this first message from Bob, it's just fixed, and that's what you have in the proving key. And so all these values are going to be in the proving key, and how large does this D need to be? It's if you want to get precise, it's like the number of multiplication gates in the circuit. So yeah, I don't have much of a recap. Basically, I tried to give a feeling for some of the ideas used in the construction of SNARKs, which are the kind of the cryptographic engine that gives you the shielded transactions. Any more questions, remarks, or requests?
I have a remark, which is that this is really awesome, and I hope we keep doing it regularly.
Oh, great. Happy to hear that.
Also, for me personally, it really helps to read the blog posts and then have questions or discussions and keep going back and forth between those two. So yeah, I really like the blog posts also.
Oh, yeah, great. Yeah, I think in general, it's you know, kind of like these first works that started this, like, yeah, with interactive, kind of this combination of, yeah, offline and interactive process. Yeah, you can learn a lot, or quickly. All right, maybe I'll just say one. Yeah.
Oh, sorry. I just noticed on chat someone asking if this
Oh,
video
good.
would be archived or uploaded somewhere, and I believe it will be. Is that true? Can Paige verify that? I'm pretty sure it will be.
Screen sharing.
I will try to make it I'll try to make sure it's archived or uploaded somewhere. Okay, sorry.
But I think, I don't know, from what I remember with the previous show and tells, I think it's kind of default that once it ends, you can just watch it on YouTube at the same.
Yeah.
Yeah,
I think
so we can just link to the
should
YouTube.
appear on YouTube.
Yeah.
Oh, I just noticed Paige can't hear us in real time, so.
Oh, because she's on the YouTube.
So we need to know when to conclude the live stream.
All right. I mean.
So what's the final part of your explainer series gonna say?
All right. So it kind of how it, like, the big picture is that you've got these first four parts about kind of how to deal with polynomials, like this blind evaluation thing. And then you've got this thing of, okay, how do you translate, like, is this transaction, is, you know, whatever you want to prove, translated into the language of polynomials? And that translation is in the part 5. And now part 6 that will come out, you know, pretty soon is about, well, how do you, okay, it kind of takes the intuitions and it explains it more, like how do you take this like blind verifiable evaluation of polynomials and really, you know, put it together and use it to prove things. But that's going to assume so that we have this kind of hiding that supports multiplication, that from e of x and e of y, you can get e of x times y. And how do you actually get such an e? Well, you do that with pairings of elliptic curves. So like the 7th and last part is going to, you know, say very little because it's a really kind of deep, you know, and complicated thing, but say a little about these pairings of elliptic curves and how they're used. So that's going to be the 7th and last part, like the.
Cool. Looking forward to it.
Okay, I'll ask to end the live stream now. Thanks a lot. See you all next time.
Okay, see you. Thanks.
I don't know yet. Not sure yet.